Ben McDonald. For my case study, I decided to do lactic acid. It's a chiral molecule that I deal with almost every single day at my job. And it's also just found very predominantly everywhere in the environment through everyday life. If you look at it, the formula is C3H6O3. The IUPAC name is 2-hydroxypropanoic acid. If you look, we have our carbon with 3 hydrogens, we have our carbon with a alcohol group, and we have our carboxylic acid. Kind of giving it that name, we start with carboxylic acid, so this is carbon 1, and then our carbon 2 is where our alcohol group is, and that's where the IUPAC name comes from. The other common name for it is milk acid. Lactic acid is produced naturally in humans. Usually when we are not making enough energy through our aerobic metabolism, our body will kick into the backup mode, which is this anaerobic metabolism, which produces lactic acid. Exercise is a very common example of when this will happen, as our body just isn't making enough energy through our aerobic metabolism, and thus it kind of kicks into this backup of anaerobic, which makes lactic acid. It's one of the reasons we think we get sore after workout, because that lactic acid has a lower pH, which can irritate our nerve endings. Lactic acidosis is another condition that will cause a elevated lactic acid value. It can be caused by a couple different things. The major ways it happens is if our body just isn't eliminating lactic acid. So that would be due to a problem with either our liver and kidneys, or if we're just making too much lactic acid. If we're making too much lactic acid, that usually means our body just isn't getting enough oxygen, which usually is caused by a heart attack, shock, or sepsis. Cyanide poisoning can also do this by just binding to the oxygen, removing our body's ability to use the oxygen. Then obviously if our liver or kidneys are damaged, they're responsible for removing the lactic acid, and thus they will, if either of them is damaged, that will also cause this buildup. Everyday life, it's also very common. In all fermented foods, lactic acid is very commonly found, just like humans. In an anaerobic environment, bacteria, yeast, fungi, and mold will also break down sugars and starches into lactic acid. Yogurt is a great example of this. Yogurt breaks down lactose into lactic acid. We also use lactic acid as a preservative in many foods. We add it in because it is a pretty acidic chiral molecule, which means that pathogenic organisms will have a harder time growing and reproducing. Same thing for disinfectants. We apply it to things to keep acidic, and so bacteria will not grow in it very well. In cosmetics, if you put it on your skin, it will help break down bonds holding our dead skin together, and it will even work as moisturizer by attracting water to it. What makes lactic acid chiral? If we look at the structure of it, we have our chiral center here. So that is our carbon with 4 different groups bound to it. Group 1 is this oxygen, this alcohol group here. Group 2 is our carboxylic acid, and group 3 is this CH3 group, and finally our group 4 is this hydrogen. Whether or not it's R or S orientation will obviously depend on whether that hydrogen is forwards or backwards orientated towards us. So on that line we have 2 enantiomers of lactic acid. The first one is L-lactic acid or S-lactic acid. That's the one that we make naturally in the body. It's way more common. It's less biologically active. It's safer. No real issues with it. The second one here is R-lactic acid. You can see the different orientations of the alcohol group. It's way less common. It's not as safe because our bodies have a harder time breaking it down. So generally, S-lactic acid is by far the preferred one. We have 2 isomers for lactic acid. We have this hydroxypropanoic acid. So that just moves the alcohol group down to the end. It doesn't really have any metabolic role in humans. It's not very biologically active. It's a precursor for certain plastics, and it's an intermediate in some pharmaceuticals, but it's not very common at all. Same thing kind of for this methyl glycolate, another structural isomer. This just adds the oxygen kind of in the middle, making this methyl group. Once more, it's not biologically active. It's an intermediate product in some esters, polymers, and chemicals, but it's also not super predominant. And here are my references. Thank you.